Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
My Weird Prompts is an AI-generated podcast produced by Daniel Rosehill, a verified human with documentation to prove it. While every effort is made to ensure our AI hosts draw from credible sources and run on cutting-edge models, they do occasionally make things up with alarming confidence. As with everything in life, and especially this podcast, treat all claims as spurious until confirmed to be not. Daniel, Herman and Corn accept no responsibility for any decisions made based on the confident ramblings of our artificial presenters. Now, today's episode.
Hi, Corn and Herman. So I'd like to send you both a question for today's podcast. We've talked in previous episodes about doing AMD on GPU, and we've talked about the two very useful technologies for isolation and dependency management, and that's Conda and Docker. Docker is, of course, very well known in general in modern computing and DevOps. Conda slightly, maybe less so, associated a lot with scientific computing and stuff that seems very complicated. I've kind of gone back and forth using both of these approaches, trying to get things to work with AMD GPU, and learned a lot in the process, but I still feel a little bit uncertain as to when it makes sense to run stuff on host, when it makes sense to use a Conda environment, and finally when it makes sense to put stuff in Docker, because depending on the project that you look at, you're going to get different answers. PyTorch, I think, official recommendation is PyTorch plus ROCm in Docker. But then I was surprised to actually look at the ComfyUI instructions more carefully and see that their recommendation is actually to create a Conda environment. So it's very confusing. You have, of course, also got regular virtual environments, but I don't feel 100% certain that I understand using all of these frequently. It's a little bit like this project says do this and I'll go with that, but I don't have an inherent grasp on what makes sense in general, and more so what the differences are exactly. But if I want to set up a Conda environment, we've talked before about reusing large packages in local AI, that you don't want to be pulling and building these massive packages like PyTorch and ROCm all the time. And no one also wants to spend their time resolving annoying dependency issues between versions of Python and these packages. So really, I think a lot of folks, I'm guessing, like me, just kind of want to figure out a formula that works relatively well. And then when we're actually trying to do stuff with local AI, whether it's using Whisper for speech to text or creating generative AI images or music or whatever the case may be, that we can kind of just roll out new services fairly easily. What you guys say, I'd love to understand the differences maybe at the real isolation level between the two, and when either approach might be more advisable.
Welcome to My Weird Prompts, the podcast where we dive deep into the fascinating questions and ideas sent to us by our very own producer and creator, Daniel Rosehill. I'm Corn, your curious guide, and as always, I'm joined by the brilliantly insightful Herman.
And it's a pleasure to be here, Corn. This week, Daniel has sent us a prompt that's incredibly relevant to anyone dabbling in local AI, especially with AMD GPUs. It touches on a pain point many developers experience daily.
Oh, I can already feel the tension. Daniel's prompt this week is all about environment management, specifically comparing host environments, Conda, and Docker when running AMD GPU workloads. He mentioned going back and forth, trying to get things to work, and feeling a bit uncertain about when to use which. He even pointed out that PyTorch and ComfyUI have different recommendations, which is causing some confusion.
Indeed, and it's a completely valid point of confusion. What seems like a straightforward choice, where do I run my code, quickly unravels into a complex web of dependency management, isolation levels, and performance trade-offs. Daniel's question hits at the heart of reproducibility and efficiency in modern computing, particularly in the rapidly evolving landscape of AI. The stakes here are wasted time, frustration, and potentially missed opportunities for leveraging powerful hardware.
So we're talking about avoiding dependency hell, right? That nightmare where one library needs Python 3.8, but another needs 3.9, and suddenly your project breaks because everything is conflicting.
Precisely, Corn. That's the core issue. When we talk about running AI models, especially complex ones that leverage GPUs, we're dealing with a stack of software. The operating system, the GPU drivers, specific versions of Python, PyTorch, or TensorFlow, various numerical libraries like NumPy, and then the AI model code itself. Each component has its own set of dependencies, and ensuring they all play nicely together is a significant challenge. Daniel wants us to explore the nuances of three primary strategies to manage this complexity: the host environment, Conda, and Docker. He's looking for a clearer picture.
Okay, so let's start at the absolute simplest level, the host environment. What exactly does that mean, and why might it be both tempting and troublesome?
The host environment, Corn, refers to running your AI application directly on your operating system, be it Linux, Windows, or Mac OS, using the Python installation and libraries that are globally available or installed specifically for your user. It's the most straightforward approach. You install Python, you install PyTorch with typeheat, and you run your script.
That sounds easy enough. What's the catch?
The catch, as you alluded to earlier, is dependency hell. While it's simple to get started, it quickly becomes unmanageable as you introduce more projects or update libraries. Imagine you have Project A that requires an older version of PyTorch and a specific CUDA toolkit, and Project B that needs the absolute latest version. If both are installed directly on your host, their dependencies will inevitably clash, leading to broken installations, obscure errors, and hours spent debugging environment variables or uninstalling and reinstalling packages. It's like trying to keep two meticulous.
So, for someone just playing around with one small thing, it might be fine, but for anything serious or multiple projects, it's a recipe for disaster. Got it. That brings us to Conda, which Daniel mentioned. He associated it with scientific computing and things that seem very complicated. Herman, demystify Conda for us. What is it, and how does it help?
Conda is a powerful open-source package and environment management system, widely used in scientific computing and data science. Think of it as creating separate, self-contained mini operating systems, but specifically for your Python, R, or even other language environments. When you create a Conda environment, you specify the Python version and all the necessary libraries for a particular project. Conda then installs these dependencies into that isolated environment, ensuring they don't interfere with your base system or other Conda environments.
So it's like giving each of those chefs their own dedicated, fully stocked kitchen, separate from the main one, so they don't step on each other's toes. That makes a lot of sense for avoiding conflicts. How does it achieve this isolation?
Exactly, Corn, a perfect analogy. Conda achieves this isolation by managing specific directories on your file system. Each environment gets its own set of executable binaries and libraries. When you activate an environment, your shell's PATH variable is temporarily modified to point to that environment's binaries first. So, when you type tpython, it executes the Python from your active Conda environment, not the system-wide Python. This is crucial for managing different versions of Python itself, which PP alone cannot do as effectively across multiple isolated instances.
And Daniel specifically mentioned AMD GPUs. How does Conda play with something like ROCm and PyTorch for AMD?
That's a key point. For AMD GPUs, the equivalent of NVIDIA's CUDA is ROCm. Installing PyTorch with ROCm support within a Conda environment is a very common and often recommended approach. Conda's ability to pull specific versions of PyTorch and ensure compatible ROCm libraries are present makes it incredibly efficient for setting up these specialized environments. Many official PyTorch ROCm installation guides specifically recommend using Conda because it simplifies the complex dependency resolution for these GPU-accelerated libraries. It can also manage the ROCm compiler toolchains needed for various operations.
So, Conda handles the dependencies. It gives you isolated environments, and it plays well with AMD GPUs. That sounds pretty good. What are the downsides or limitations of Conda?
While Conda is excellent for managing software environments, its isolation is at the application level, not the operating system level. This means it still relies on the host's underlying OS, kernel, and system-wide drivers. For instance, your AMD GPU drivers must be correctly installed on the host system first. Conda cannot install or manage those low-level drivers. Another minor drawback can be the disk space taken up by multiple, full Conda environments, as each can contain many duplicate packages. Also, while it isolates software dependencies, it doesn't isolate system resources or provide a fully reproducible operating system-like environment for deployment or sharing across different host OS types.
Okay, now for Docker. This is something many people have heard of, especially in the context of modern computing and DevOps, as Daniel put it. Herman, how is Docker different from Conda, and what level of isolation does it provide?
Docker takes isolation to the next level entirely. Instead of just managing software packages within an existing OS, Docker provides containers. Think of a container as a lightweight, standalone, executable package that includes everything needed to run a piece of software: the code, a runtime, system tools, system libraries, and settings. It essentially bundles a miniature operating system environment, isolated from the host OS, except for the kernel. This means Docker provides OS-level process isolation, memory isolation, and file system isolation.
So, it's not just a separate kitchen, it's like a whole separate self-contained food truck, with its own mini-kitchen, its own water supply, its own everything, ready to be driven anywhere?
That's an excellent analogy, Corn. A Docker container is highly portable. You can build a Docker image once and then run it on any system that has Docker installed, knowing it will behave exactly the same way, regardless of the host's specific Python version, library installations, or even what base Linux distribution it's running. This is a massive boon for reproducibility and deployment. Developers often use Docker files, which are text files that contain instructions for building a Docker image, ensuring that the environment is precisely defined and rebuildable.
That sounds incredibly powerful for consistent results and sharing. But how does this level of isolation interact with something like a GPU? That seems like it would be a challenge.
You've hit on a critical point, Corn. Accessing host hardware like GPUs from within a Docker container requires specific configuration, often referred to as GPU pass-through. For NVIDIA GPUs, this is handled elegantly by NVIDIA Container Toolkit, formerly NVIDIA Docker. For AMD GPUs and ROCm, it's similar but requires using the AMGPU Docker plugin or ensuring the appropriate device-device flags are passed to the docker run command, along with ensuring the host system has the correct ROCm drivers installed. The container itself doesn't install the drivers, it leverages the host drivers. This is often the trickiest part for new users.
So, Daniel mentioned PyTorch, recommending PyTorch plus ROCm in Docker. Why would they prefer that over just Conda?
The PyTorch recommendation likely stems from the benefits of Docker for deployment and reproducibility at scales. For a production environment, or when sharing complex research environments, Docker offers unparalleled consistency. A PyTorch model trained in a Docker container can be deployed to a cloud server or another developer's machine with high confidence that it will run without environment-related issues. For AMD GPUs specifically, the ROCm stack can be complex to manage across different host OS versions, and Docker provides a stable base image where the ROCm libraries are pre-configured for a known.
And then Daniel noted that ComfyUI, a popular stable diffusion UI, actually recommends creating a Conda environment. That seems to contradict the PyTorch recommendation. What's going on there?
This is where Daniel's confusion is perfectly understandable, and it highlights the project-specific nature of these choices. ComfyUI, while utilizing PyTorch and GPUs, is typically used as a local application for generating images. For this use case, Conda offers a lighter weight and often simpler setup for a single user on their local machine. Creating a Conda environment for ComfyUI allows users to keep its dependencies separate from other Python projects without the added complexity or overhead of Docker.
So, if I'm building a massive, distributed AI training system, Docker is my friend. But if I'm just running a local app to generate images, Conda might be simpler.
That's a good simplification. Docker excels when you need strong isolation, guaranteed reproducibility across different machines, packaging for deployment, or when working in a team where everyone needs the exact same environment. Conda is generally easier for setting up development environments on a single machine, managing multiple Python projects, and for scientific users who need to swap between specific versions of data science libraries without heavy overhead.
Okay, let's really dig into the real isolation level. Daniel asked about, how do these three approaches differ fundamentally in what they isolate?
Absolutely. 1. Check host environment provides virtually no isolation for software dependencies. Everything installs globally or within your user's space, leading to potential conflicts. Hardware access is direct. Check Conda environment isolates software dependencies, Python versions, libraries at the application level. It creates separate directories for packages and modifies your shell's PA checks. It relies heavily on the host OS for everything else: kernel, drivers, system libraries. Hardware access is still direct from the perspective of the application, but mediated by the host OS. 3. As Docker container provides OS-level isolations for processes, files.
That's a really clear distinction. So, Conda isolates the specific Python packages and their versions, while Docker isolates an entire miniature OS environment. This makes me wonder about hybrid approaches. Can you use Conda inside Docker?
You absolutely can, and it's a very common and powerful pattern. This is where you get the best of both worlds. You can build a Docker image that has a base operating system, the necessary GPU drivers configured, and then inside each GPU drivers, you create and manage your specific Python environments using Conda.
Why would someone do that? What's the benefit?
The benefit is twofold. Docker provides the robust, portable, and reproducible outer shell that ensures your entire environment, OS, system libraries, and even the Conda installation itself is consistent everywhere it runs. Then, Conda within that container gives you the flexibility to easily manage different Python environments for various experiments or sub-projects inside that consistent Dockerized base. For instance, you could have a single Docker image for your AMD GPU development, and within that, different Conda environments for PyTorch 1.yen10, PyTorch 2.yen, TensorFlow, or specific research projects, all without having to rebuild the entire Docker.
That's brilliant! It takes the sting out of rebuilding huge Docker images just for a Python package change. So, for Daniel's question about a formula that works relatively well for local AI, especially with AMD GPUs, how would we synthesize this into actionable advice?
T for Ropper, Ropus Rapacis tap initially, then eschly, then eschies, per ver Ropus plus tax. Con the n sax tax, or R propers the super or okay with the super or robust repropers tex eckers tecker, x throw or robust reproducts emeg tecker, opros tex, throw proper stecker, okra proper stecker, crop proper zicker, upper zicker, proper zicker, opera zicker, first, proper zicker. Roppers, the croppers, zucker, proppers, the croppers, sickerver, cropper, suckers, the crop of roppers.
That clarity is extremely helpful. So, it's not a one-size-fits-all answer, but rather a decision based on the specific use case, team size, and deployment needs. Herman, are there any lingering questions or future implications Daniel and our listeners should keep in mind?
Absolutely. The landscape of GPU computing and environment management is constantly evolving. What works best today might shift tomorrow. For instance, technologies like Singularity Apptainer offer containerization solutions tailored more towards high-performance computing clusters, which might be relevant for some. Also, the integration of ROCm into various frameworks is continuously improving, meaning some of the setup complexities might ease over time. Daniel's formula should remain adaptable. The key takeaway is understanding the levels of isolations each tool provides and matching that to your project's specific requirements, rather than blindly following a single
Herman, that was incredibly insightful. Daniel's prompt truly allowed us to dissect a very common developer challenge, and your explanation of host environments, Conda and Docker, along with their interactions with AMD GPUs, was crystal clear.
My pleasure, Corn. It's a complex area, but crucial for anyone serious about local AI development.
And to Daniel, thank you for yet another fascinating and highly practical prompt. Your questions really push us to explore the nuances of modern computing. To all our listeners, we hope this discussion helps you navigate your own environment management challenges. You can find My Weird Prompts on Spotify and wherever else you get your podcasts. We'll be back next time with another weird and wonderful prompt.
Until then, happy computing!
Goodbye. Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.